Okay, this is my video on the pulley drive system on the trainer here in the lab. So the first thing to do was check for alignment. Basically, visual check shows it's fairly in line. It's a little off, but for our purposes, it's aligned well enough. Ways to check this would be by using these rails, measurements between the rails, and the distance here, the distance of the pillow block bearings here and here versus the rails here, and the distances here and here. You could use those to make sure you're aligned, as well as make sure that your pillow block bearings are in line so that your shaft isn't cantered this way or this way, which would also affect how your belt's riding on the pulley. The power source for this system would be from the motor. The motor is getting its power from the VFD, which you can use to adjust the speed of the motor. And then what is transferring power? So from the rotation on the motor shaft, the coupling is transferring power to the other shaft, which is running through the bearings, and then this shaft is transferring power to the pulley via the keyway, which is driving the pulley, and then this pulley is transferring force to the second pulley via the belt and friction of the belt on the pulley, and then this pulley is transferring power to this shaft also via the keyway, which is driving this shaft, which you could then connect another machine or part to. Is there any incorrect components? I'm not seeing any incorrect components on this. Okay, then we calculated the belt tension and belt length. The belt tension was calculated with a belt tensioner. So you have to have the span distance of the belt span, which is essentially from the center to center where the belt comes off of each pulley, and then you use this tool to set, based off of that span distance, you set this lower O-ring and place it on there, and then as if there was a line traveling there and there, you would line that O-ring up with that line, and then you get your tension readout on the top here. When we did that, we got around 3 to 4 pounds of tension on this belt. And then to calculate the belt length, you need the center to center distance on the shafts, and then the pulley diameters, and then that would be plugged in to an equation out of the machinery's handbook. And this belt is a 40-inch belt. My calculation came out to approximately that. Okay, then, so we'll run the system to make sure. So we'll pull off the lockout, engage the disconnect, make sure everything's clear, there's no parts or anything caught in the machine. VFD's running. I'll put it into forward. and take off the emergency stop and hit go. So now we're rotating. You can see there's a little bit of an alignment issue. Alright, we'll stop it. So then to calculate the mechanical advantage, I'm gonna turn the system off. To calculate the mechanical advantage, what we did was use the string, and we pulled off the belt, and we ran a string inside each sheave, and then got the inner circumference, and used that to calculate the diameters. And then we used that and divided the input by the output. That came out fairly close. And we also found the numbers on the sheaves themselves, which we figured is probably the radius in millimeters. So we had 60 on this and 36 on this. When you divide the input by the output, that gives you a mechanical advantage of 1.66 repeating. So in this system, we have the larger sheave driving the smaller sheave, so that would mean that speed is being amplified on the output end. So we determined that then using the flight tachometer, and when we used that as it was spinning, we got a speed of 868 RPM on the smaller sheave and 538 RPM on the larger sheave. And then when we ran that calculation for mechanical advantage by dividing the 868 by the 538, it came out to 1.61, so that was fairly close to the 1.6 repeating. And that should wrap up the video. Thanks for watching.